On August 12th, 2026, a massive, fast-moving shadow will touch down on Earth, marking a truly rare celestial event, a total solar eclipse. This specific alignment hasn't cast a shadow of totality over mainland Europe since 1999. For millions of observers, this brief window of daytime darkness will be a once-in-a-generation experience. But catching the full spectacle requires precision. Your exact geographic location dictates entirely what you will see in the sky. Step inside that narrow path of totality, and an otherwise ordinary Wednesday afternoon turns into an unforgettable, sudden twilight. We can trace the journey of this shadow starting in North America. The northern regions of the United States and Canada will catch the outer edge, treating observers to a partial eclipse. This map illustrates the geographic rule. The further north you travel, the deeper the eclipse becomes, solar coverage increasing dramatically. That trajectory creates a distinct phenomenon in Alaska, where the eclipse perfectly aligns with the break of day. The sun will pull itself over the horizon already partially obscured, looking like a crescent carved out of the morning. Even thousands of miles from totality, sitting at the very periphery of the shadow, the normal rhythm of morning light is noticeably disrupted. The true core of the eclipse, however, tracks much further north. The darkest part of the shadow first makes contact across the frozen waters of the Arctic Ocean. From there, the relentless path of totality sweeps down over the remote, icy expanses of Greenland. Moving rapidly southeast, the shadow soon reaches Iceland, plunging its jagged volcanic coastlines into absolute daytime darkness. And the sheer scale of the surrounding penumbra is massive. Even outside that path of totality, observers across the United Kingdom and Ireland will see over 90% of the sun covered by the moon. It is a relentless, moving force that momentarily freezes vastly different, extreme landscapes under the exact same cosmic twilight. Eventually, the shadow makes its way to mainland Europe, crossing a very narrow band of northern Portugal. But among all these locations, Spain stands out as the climax of the trajectory. Unlike the sunrise event in Alaska, the timing here aligns with the evening. The eclipse perfectly coincides with the golden hour. The visual payoff could be extraordinary, a completely blackened sun hovering incredibly low on the horizon, just moments before sunset. This specific geometry casts an unforgettable sky, blending the warm, colorful glow of a twilight horizon with the deep, cold darkness of totality directly above. Yet to fully appreciate the mechanics driving this beauty, we have to look past the scenery. Tracking this spectacular shadow across the globe is only the first step. To truly grasp the event, we need to understand what a solar eclipse actually is. A solar eclipse is a specific physical event occurring at the moment the moon passes directly between the Earth and the sun. This three-body geometric alignment is only possible during the new moon phase of the lunar orbit. In the days leading up to this transit, the moon is effectively invisible from Earth, hidden by the intense glare of the sun. The moon completes its orbital cycle, returning to this new moon phase roughly every 29.5 days. Because the moon reaches this position every month, we might expect a solar occlusion to be a regular 29.5-day occurrence. The reason it is not comes down to the requirement for a perfect alignment versus the actual three-dimensional layout of our solar system. In a simplified two-dimensional model, the moon's shadow would fall across Earth every orbit. But the lunar orbit is actually inclined by 5 degrees to Earth's plane. This causes the moon to transit slightly above or below the sun during most new moons. A solar eclipse is a rare exception to standard lunar cycles, occurring only when the Earth, moon, and sun meet at a precise, multivariable intersection of orbital planes. That intersection occurs along the line of nodes, where the moon's tilted plane crosses Earth's orbital plane. For an eclipse, the moon must cross this line exactly during the new moon phase. This alignment, syzygy, is the threshold condition to trigger an eclipse. Once that baseline alignment is achieved, the visual outcome depends on the centering of the transit. In a partial solar eclipse, the moon and sun are slightly off-center, and the moon covers only a fraction of the solar disk. In totality, a direct central alignment allows the moon to block the solar photosphere completely. This poses a physical question. How can a satellite as small as the moon occlude a massive host star? While nodal alignment permits an eclipse to happen, a secondary geometric coincidence is required to permit totality. There is a vast physical size discrepancy between the Earth's moon and the Sun. The Sun's physical diameter is approximately 400 times larger than the diameter of the moon. But the moon is also much closer to our perspective. The Sun is positioned approximately 400 times further away from Earth than the moon. In observational astronomy, we measure apparent angular diameter, the slice of sky an object occupies. Because the distance ratio mirrors the size ratio, the physical difference is canceled out from our surface perspective. Consequently, both celestial bodies occupy roughly 0.5 degrees of the sky. This exact geometric equivalence allows the moon's disk to perfectly match the boundaries of the Sun. This visual matching creates the complete occlusion of totality during a central transit. Totality is an optical phenomenon born entirely from this exact 400 to 400 spatial ratio. Because of orbital eccentricity, this 400 to 400 ratio is not perfectly static. The lunar orbit is elliptical, causing its physical distance from Earth to vary throughout the month. The specific point where the moon is closest to Earth is called perigee. The furthest point is apogee, establishing the boundaries of this orbital variance. These variances dictate the specific parameters of the 2026 total solar eclipse. During the 2026 syzygy, the moon will be positioned near its perigee. Because the moon is nearer to Earth, its apparent angular diameter increases slightly beyond the baseline 0.5 degrees. This larger angular diameter physically widens the umbral cone, the darkest part of the shadow, as it intersects the Earth. This wider shadow results in an extended duration of totality on the ground, projected to exceed 2 minutes in some locations in 2026. Orbital eccentricity acts as a modifier to the 400 ratio, determining whether an eclipse is a fleeting event or a sustained phenomenon. These variables, nodal alignment, the 400 ratio, and the moon's distance, combine to project a single physical shadow onto Earth. The path of totality is the track etched by this moving umbral shadow. It is remarkably narrow relative to Earth's surface area. As it moves, Earth's spherical shape interacts with the flat shadow cone, distorting it at higher latitudes. Earth's rotation further complicates this, sweeping geographic locations through the shadow at varying speeds. Because of these interacting geometries, totality is not experienced uniformly across the globe. Locations on the extreme outer edges of the path experience a significantly shorter duration of totality. Only coordinates directly on the center line of the shadow path achieve the maximum duration. There is a severe observational difference between standing inside the deep umbra versus the surrounding penumbra. Moving just a few miles outside the mathematical path breaks the optical effect of the 400 ratio. Inside the exact zone of totality, observers witness a sudden, dramatic environmental shift as the landscape plunges into twilight. Experiencing a total eclipse is the proof of these precise orbital mechanics, requiring the observer to stand at the exact point where the lunar shadow intersects the Earth during the peak of syzygy. When the moon aligns perfectly between the Sun and the Earth, it casts a massive shadow across our planet. It is a rare alignment of science, timing, and nature. But while this is a cosmic event, your personal experience comes entirely down to earthly geography. Where you stand dictates exactly what you will see in the sky above you. You face a clear choice: position yourself to witness a 100% total eclipse, or stay put and settle for a partial one. They are completely different phenomena. Making the wrong choice or ignoring the physical reality of the event carries severe consequences. Looking directly at the sun without protection permanently damages your eyes. Your exact coordinates will dictate both the specific visual phenomena you witness and the strict survival rules you must follow to keep your vision intact. Viewers often falsely assume that a 99% partial eclipse offers 99% of the experience. Even at 99% coverage, the sky never fully darkens. The sun's powerful remaining fraction still bathes your surroundings in ambient daylight, but achieve 100% totality and the sun completely disappears. The temperature drops, and for a brief moment, day turns dramatically into night. This sharp visual divide also creates a strict divide in safety protocols between the partial and totality zones. If you are in the partial zone, certified solar eclipse glasses are essential. They filter harmful rays and must be worn the entire time. If you are inside the path of totality, however, there is a narrow window where you can safely remove your glasses to look with your naked eye, only when the moon completely covers the sun. You will recognize this safe window by the diamond ring effect. Before totality ends, a bright flash of sunlight bursts at the moon's edge, signaling that your glasses must go back on immediately. That 1% of coverage makes the difference between a dim daytime curiosity requiring constant safety gear and an immersive nighttime blackout you can watch with your own eyes. This map shows the layout of Western Europe during the eclipse, divided into two distinct viewing zones. The first path is the narrow band of 100% totality, tracking straight through Spain. Cities like Bilbao, Santander, Zaragoza, and Valencia fall directly under the complete blackout. Bilbao stands out as a primary destination for observers wanting the full experience of totality. Further south along the path, Valencia offers another prime staging ground, where the sun will completely vanish. Outside of Spain, the only other place to see the complete eclipse is a very small region in northern Portugal, right near the border. Reaching these specific coordinates introduces heavy logistical friction. You will navigate dense crowds, high travel costs, and the need for rigorous advanced planning. Accepting those hurdles grants you the exclusive reward of the complete naked-eye nighttime blackout. Choosing the totality zone requires high effort, but it guarantees the absolute maximum experiential payoff. Returning to our map, the second branch covers the much larger partial viewing zone. This includes the UK, Ireland, and major Spanish cities outside the direct path, like Madrid and Barcelona. In the Republic of Ireland, the partial views will be highly impressive during the early evening hours, with Dublin seeing up to 94% coverage and Cork reaching 96%. For residents along the River Liffey in Dublin, stepping outside your door offers a highly accessible near-total view. Down in Cork, the view is slightly deeper, peaking about 1 hour after the event begins. Meanwhile, large hubs like Madrid will remain comfortably in the partial zone. Observers there will miss the true blackout entirely. This is the trade-off. You gain ultimate geographic convenience by viewing from home, but you are confined to unbroken safety gear requirements, and you will see no nighttime effect. Staying put is a practical choice that saves time and money, provided you abandon any expectation of experiencing a full blackout. Regardless of your location, the biological risk is severe. Looking straight at the sun without certified protection will permanently damage your retina. If you want a closer view than standard eclipse glasses allow, there are alternative ways to safely magnify the event. Solar telescopes or specialized lens filters allow you to safely observe the sun's surface and the moon's silhouette in sharp detail. But this equipment requires exact specifications and rigorous adherence to safety protocols. Do not attempt this without proper guidance and verified filters. Whether you use simple cardboard glasses or complex optical scopes, you must treat your safety equipment as critical life support gear, not an optional accessory. This chart maps logistical effort against experiential impact. Observing a partial eclipse from home requires incredibly low effort, but the overall impact stays lower. Traveling into the path of totality in Spain or Portugal demands maximum effort, but unlocks the highest possible astronomical impact. If you choose the path of totality, remember, your protective glasses come off only during those brief, specific minutes of total darkness. If you remain outside that path, there are no exceptions. Certified solar glasses are non-negotiable for the entire duration. A solar eclipse rewards preparation. The cosmos provides the spectacle, but you alone are responsible for where you stand and how safely you observe it.